All right, our drawing shows 3 blocks interacting, okay? So the problem reads, the drawing shows box 1 resting on a table. I guess the problem reads 1, 2, and 3. I made A, B, and C, so we'll change that. The problem reads box 1 is resting on the table. There's our box 1. Box 2 is resting on top of box 1. And box 3 is hanging by a massless rope and a frictionless pulley. All right, one end of box 3. Okay, the masses of the 3 boxes are, the mass of box 1 is equal to 5.6 kilograms. The mass of block 2 is equal to 3.6 kilograms. And the mass of block 3 is equal to 2.9 kilograms. So if this is in a state of equilibrium, so nothing is moving, what is the normal force on block 1? So what is the force that the table exerts on block 1? So the force the table exerts on block 1, the normal force on block 1. All right, so we have interacting objects here, multiple interacting objects. We are interested in the force that the table is exerting on block 1. So let's go after block 1, see what we need to solve this problem. So we are going to look at a free body diagram of block 1, thinking about all the interactions. Okay, well we know that gravity is interacting with block 1, so we'll do a little force tree here. That's between block 1 and the earth. And we know that that points in the downward direction, and it's equal to the mass, block 1 times gravity. Okay, well, the block is also interacting with the table, so we have that normal force. So that's between block 1 and the table. All right, we also know that block 1 is interacting with block 2, so we'll call that the force of block 2 on 1. And that's between block 1 and block 2. And what direction is that force? Well, the block 2 is on top of block 1, so that force is in the downward direction. And we can see that my arrows are not necessarily representative of what this situation might look like. I'm going to make my normal force look a little bit better with respect to the problem. All right, any other interactions on block 1? Not really. So I think this is it. Now we recognize right away that this is only in the vertical direction. And it's the earth vertical, so we can call it normal vertical. Now I'm going to number my forces, 1, 2, and 3. All right. And so for force number 1, well, that's in the downward direction, m1 times g. Force number 2, that's in the upward direction, so that's a positive normal force on block 1. We're going to call that the normal force on block 1. And force number 3, well, that's in the downward direction, block 2 on 1. Okay, so like our force analysis has us do, we're going to look at the sum of these forces in the vertical direction. The mass times the acceleration in the vertical direction, that of course is 0 if these forces are in equilibrium. And we have minus m1g plus n1 minus f2 on 1 is going to equal to 0. Now we wanted that normal force, so let's solve for the normal force. So we're going to bring everything else over. The normal force is going to equal the force of 2 on 1 plus mg. Now we're given the mass of 1, and that is 5.6. So this leaves us with our normal force equal to the force of 2 on 1 plus 54.88. So I need the force of 2 on 1. Well, those are interacting objects, so the force of 2 on 1 is equal to opposite the force of 1 on 2. So let's look at block 2. All right, so we're going to analyze block number 2. Because if I could get the magnitude of the force that block 1 exerts on block 2, I have the magnitude of the force that block 2 exerts on block 1. Keep in mind that we've already considered direction here, so this truly is just a magnitude in our relationship down there. All right, so let's look at that free body diagram on block 2. Again, we know we have the force of gravity between block 2 and the earth, and that points in the downward direction. So that's m2 times g. The string, well, that's interacting with block 2. So we have the tension on block 2, and that's between block 2 and the string, and that's kind of pulling up. Tension on block 2. And then, of course, there's this interaction between block 2 and 1. And it was down block 2 on 1, so it must be up. And we can sort of visualize that for the force block 1 on 2, which is equal in magnitude of the force of block 2 on 1, which is what we were going after. And we see it's in the opposite direction. Perfect. So let's look at the forces. Again, they're all in the vertical direction, earth vertical, so we can identify them that way. We're going to label them 1, 2, and 3. And force number 1, well, that's the downward direction, mass 2 times g. Force number 2, well, that's in the positive direction, the tension on block 2. And force number 3, well, that's in the positive direction, the force interaction between 1 and 2. And I'm going to put 2, 1 because that's what I knew I needed here. All right, so let's look at that sum. In the vertical direction, well, there's no motion in the vertical direction, so the acceleration, there's also no acceleration if there's no motion, must be 0. So we have minus m2g plus the tension plus the force of 2 on 1 is equal to 0. And I was going after this force here, so let's solve for it. We have the force of 2 on 1, which is the same as force of 1 on 2, is equal to m2g minus T2. I'm given the mass of block 2 at 3.6. So I know the force of gravity is equal to 35.28 minus, I don't know that tension, so I need T2. All right, well, go back to the drawing board. What is T2 related to? Well, it's the tension in the rope. So we look for what else is that rope interacting with. That rope is interacting with block 3. So we start our analysis on block 3. Remember, the physics is always sort of telling you, I just noticed I did not put that last force in. The physics is always sort of guiding you onto what you need. So let's look at block 3. Well, block 3 is interacting with the force of gravity. So the force of gravity on block 3 is between block 3 and the earth. And that points in that downward direction. And we have the tension force pointing in the upward direction on block 3. And since it's the same rope, T3 equals T2. All right, so let's look at that. We only have our vertical forces. We will identify them as force 1 and force 2. Oh, and remember our tension 3 is between block 3 and the rope, or string. All right, so we'll call it the string. That's what I did for block 2. Okay, so block 3, our first force, the vertical force, the force of gravity. So we have minus m3 times g. And our second force, well, that's just the tension. We'll go with tension 2 because we want to relate it to the same, which is equal to tension 3 in the upward direction. So looking at the sum of our forces in the vertical direction, well, there's no change in motion vertically, so those, in fact, will sum to 0. And we have tension 2 minus m3 times g is equal to 0. So my tension is equal to m3 times g, and we're given the mass block 3 as 2.9 times 9.8, which is 28.42 newtons, which means that my tension in block 3 is 28.42. I can put that in there, and I find that my force of block 1 on 2, or 2 on 1, is 35.28 minus 28.42, 6.86 newtons, and I can put that in here, and we find our normal force on block 1 is equal to 61.74 newtons. All right, so recognizing that we need to be doing an analysis of what we want, which is that normal force, block 1. In order to do that, I need to understand something about block 2. In order to do that, I need to understand something about block 3, and then it winds its way back. So our solution is that the tension, the normal force on the block, is equal to 61.74. Now I was just verifying that with the key. All right, nicely done.